Your car is burning oil between changes. Not leaking it, burning it. You check underneath and the driveway is clean. No puddles, no drips, no obvious seals weeping. But every 1,000 miles you are adding half a quart. Every 2,000 miles you are adding a full quart. Your exhaust smells faintly of burnt oil under hard acceleration. Your spark plugs are fouling faster than they should. And the mechanic you took it to told you one of three things: your piston rings are worn, your valve stem seals are gone, or your engine is just old and this is normal. He quoted you anywhere from $1,500 to $6,000 depending on which diagnosis he landed on. Here is what he almost certainly did not check: the intake manifold runner control system, specifically the tumble flap actuator and its position sensor. On most modern direct injection engines built between 2004 and 2022, this single component, which costs between $45 and $180 depending on the manufacturer, creates a failure pattern so closely mimicking piston ring wear and valve stem seal failure that it is misdiagnosed constantly, in every country, by experienced mechanics who simply never learned to look for it. By the end of this video, you will understand exactly what this system does at a physics level, exactly how it fails, exactly how to diagnose it correctly with nothing more than a scan tool and your own eyes, and exactly how to fix it yourself before it causes secondary damage that actually does cost thousands of dollars to repair. What the intake manifold runner control system actually does. Every internal combustion engine needs air to move through the intake ports in a specific pattern to mix efficiently with fuel. This is not simply about volume, it is about velocity and turbulence. An air charge that enters the combustion chamber in a controlled spiral, called a tumble or swirl pattern, mixes with fuel far more completely than an air charge that enters in a straight, undirected column. More complete mixing means more complete combustion. More complete combustion means more power extracted from every milliliter of fuel, lower emissions, and less unburned fuel washing down the cylinder walls and contaminating the oil. The intake manifold runner control system, called IMRC on Ford engines, IMCS on Mitsubishi, variable intake system or DISA on BMW, variable induction system on Mazda, and ASIS on Toyota, manages this process through a set of butterfly valves or tumble flaps mounted inside the intake manifold runners, one per cylinder. These flaps are thin, precisely machined aluminum or composite blades roughly 20 to 30 millimeters wide that sit perpendicular to the airflow at low RPM, forcing incoming air to travel around them and enter the combustion chamber in a controlled swirl pattern. As engine RPM rises and the cylinder demands more air volume than the restricted opening can supply, the flaps rotate open on a shared shaft controlled by a vacuum actuator or an electric servo motor, removing the restriction entirely and allowing full unrestricted airflow. The position of these flaps is monitored continuously by a position sensor that reports back to the engine control unit. The ECU cross-references flap position against RPM, manifold absolute pressure, throttle position, and coolant temperature to determine whether the system is responding correctly. When it is not, when the flaps stick, when the actuator loses vacuum, when the position sensor drifts out of calibration, when the plastic linkage that connects the actuator rod to the flap shaft cracks or seizes, the ECU logs a fault and in many cases enters a fuel trim compensation strategy that partially masks the performance loss, making the problem harder to identify by feel alone. Step 1. Understand why this specific failure burns oil. This is the part nobody explains, and it is the key to understanding why this failure is so expensive when it is ignored. When the tumble flaps fail in the closed position, which is the most common failure mode because the carbon deposits that accumulate on direct injection intake manifolds also accumulate on the flap blades and their pivot points, gradually seizing them in place, the cylinder receives a severely restricted air charge at all RPM ranges, not just at low RPM where restriction is intended. The cylinder is now trying to complete a combustion cycle with less air than the fuel injection system is delivering. The mixture goes rich. Combustion is incomplete. Unburned fuel accumulates on the cylinder walls. Here is the critical physics. Engine oil sits in a thin film on the cylinder walls, approximately 5 to 10 microns thick under normal operating conditions, to lubricate the piston rings as they travel up and down. This oil film is burned off during the combustion event in tiny, controlled quantities that the engine is designed to handle. When the combustion event is incomplete due to a rich mixture from restricted airflow, the combustion temperatures drop below the threshold needed to fully combust that oil film. The unburned oil exits through the exhaust. Your oxygen sensor detects a rich condition and the ECU pulls fuel, which partially corrects the mixture reading but does not address the root cause. Your exhaust smells of burnt oil. Your spark plugs show a characteristic wet, dark fouling pattern on the electrode that mechanics associate with valve stem seals, but that in this case is being caused by the incomplete combustion from the starved air charge. Simultaneously, the unburned fuel that is washing down the cylinder walls is diluting your engine oil, reducing its viscosity, and accelerating wear on your main bearings and rod bearings. An engine that appears to be burning a quart of oil every 1,500 miles due to this failure mode is actually experiencing oil dilution from fuel contamination as a secondary consequence, meaning the oil you are adding is not all being burned, some of it is being displaced by fuel that has no business being in the crankcase. This is why ignoring the intake manifold runner control failure long enough eventually does produce genuine piston ring wear and genuine bearing wear. The misdiagnosis becomes a self-fulfilling prophecy. Fix the flaps early and your engine is fine. Ignore the flaps for 40,000 miles and you eventually do need the $4,000 engine job. Step 2. Pull the fault codes correctly. A generic OBD2 code reader will tell you almost nothing useful here. The codes generated by intake manifold runner control failures are stored as manufacturer-specific codes in the enhanced diagnostic memory, not in the generic OBD2 memory that a $30 Bluetooth scanner reads. The codes you are looking for vary by manufacturer. On BMW engines using the DISA system, look for fault codes 2A63, 2A67, or 29CD in the DME fault memory, which require either ISTA diagnostic software or a professional-grade scan tool like Automaxis, LaunchX 431, or VCDS for VAG vehicles to read correctly. On Ford engines with the IMRC system, you're looking for P1000 series codes, specifically P1516, P1517, P1518, which indicate intake manifold runner control stuck open, stuck closed, or circuit malfunction respectively. On Mazda and Mitsubishi applications, look for P2004, P2005, P2006, P2007, P2008, and P2009, which correspond to individual runner control valves by bank and cylinder position. If your scan tool shows any of these codes alongside fuel trim codes, specifically long-term fuel trim values more than plus 10% or minus 10% on either bank, you have confirmation that the runner control failure is affecting combustion quality significantly enough that the ECU has been compensating for it over an extended period. Long-term fuel trim values this far outside normal range on a car with no vacuum leaks and a relatively new mass airflow sensor are one of the clearest indicators in all of engine diagnostics that something is fundamentally wrong with the air charge entering the combustion chambers. Step 3. Perform the visual inspection. With the engine cold, remove the intake air duct between the air filter box and the throttle body. Use your flashlight to look through the throttle body bore into the intake manifold runners with the throttle plate held open by hand. On most engines you can see at least partially into the runner passages from this angle. What you are looking for is carbon. On direct injection engines, any engine where the fuel injectors spray directly into the combustion chamber rather than into the intake port, the intake valves and manifold runners receive no fuel washing over them between combustion events. The hot combustion gases that flow back through the intake during valve overlap carry oil vapor from the PCV system, and without fuel to dissolve and wash this vapor away, it bakes onto the intake valve heads and runner walls as hard carbon deposits. On a direct injection engine with 60,000 miles or more, the carbon buildup on the intake valves can reach 3 to 6 millimeters thick, enough to reduce intake valve flow area by 15 to 25% even before accounting for any flap restriction. If you can see into the runners, look for the tumble flap blades. With the engine off and cold, they should be in the closed or partially closed position. Use a long, thin wooden dowel, never metal, which could scratch machine surfaces, to gently push against the flap blade. It should move smoothly and with minimal resistance through its full range of travel. If it does not move, or moves stiffly and then stops, the pivot shaft is seized in its bore, almost certainly from carbon accumulation on the shaft journals and in the actuator linkage mechanism. Step 6. Address the carbon on the intake valves simultaneously. Cleaning or replacing the runner control system without addressing the carbon on the intake valves is solving half the problem. The carbon deposits that seized your flap shaft came from the same source that is coating your intake valves: oil vapor from the PCV system baking onto hot metal surfaces in the absence of fuel washing. The correct method for removing intake valve carbon deposits without removing the cylinder head is walnut shell blasting, a process where a media blaster loaded with crushed walnut shell media is inserted through the spark plug bore or the intake port with the valve held open, and the hard shell media is blasted against the carbon deposits at high velocity. The walnut shell is hard enough to fracture and remove polymerized carbon but soft enough that it cannot damage the precision-machined valve seat, valve face, or port walls. This process requires removing the intake manifold to access the ports directly and takes between 2 and 4 hours for a complete 4-cylinder engine, or 4 to 6 hours on a V6 or V8. If walnut blasting is not feasible immediately, a partial chemical decarburization can be achieved by introducing leaky moly valve clean or BG44K intake system cleaner into the airstream upstream of the throttle body with the engine running at 2000 revolutions per minute using the controlled application method described on the product packaging. This dissolves a portion of the carbon deposits, typically 30 to 50% of accumulated deposits in a single treatment, and burns them off through the exhaust. You will see white smoke from the exhaust during this process. This is normal and expected. The smoke is vaporized carbon solvent carrying dissolved carbon deposits out of the engine. It will clear within 10 to 15 minutes of completing the treatment and should not return. The real prevention strategy. Everything described in this video, the carbon seizure, the oil burning, the fuel trim compensation, the accelerated bearing wear, is a consequence of one fundamental engineering reality of direct injection engines that the automotive industry communicates very poorly to buyers. Direct injection engines require a walnut blast intake valve cleaning at intervals of 40,000 to 60,000 miles as scheduled maintenance, not as a repair. This is not an opinion. Volkswagen, Audi, BMW, Mercedes-Benz, and Hyundai have all published technical service documentation acknowledging carbon accumulation on intake valves as a characteristic of direct injection combustion architecture. The interval varies by application, by oil quality, and by how often the engine reaches full operating temperature. Short trip driving where the engine never fully heats up accelerates carbon accumulation significantly because the PCV system produces more condensation at low operating temperatures. Use only full synthetic oil with a viscosity grade matching your manufacturer's exact specification. A 5W30 engine with a 0W20 full synthetic installed does not gain protection. It loses it, because the reduced viscosity at operating temperature allows more oil vapor to pass through the piston ring package and enter the crankcase ventilation system. Specification compliance matters more than brand loyalty. Change the PCV valve or clean the PCV system, including all associated hoses and the oil separator if your engine uses a separate catch can style separator, at 60,000-mile intervals. The PCV system is the source of the oil vapor that creates every carbon deposit discussed in this video. A functioning, flow-controlled PCV system produces manageable quantities of oil vapor. A degraded, stuck-open PCV system floods the intake manifold with oil mist under all operating conditions and accelerates every failure mode described here by a factor of 2 to 3. The intake manifold runner control system, the intake valves, the PCV system, and the combustion quality of your engine are not separate problems. They are one interconnected system. When one degrades, the others follow. The mechanics who understand this at a genuine engineering level and who explain it to their customers are exceptional. Most will treat each symptom individually, charge you for each individual repair, and send you on your way without ever connecting the dots. Now you have connected them yourself. Use that knowledge every time someone quotes you a repair bill. If this gave you information you did not have before, like this video. Subscribe if you want this level of technical depth every week. And drop a comment telling me your engine code and your current symptoms. I answer everyone personally, and I will tell you exactly where to start on your specific car.